So basically the first step, obviously, before doing anything is you want to check the nameplate on the motor, sticker on the drive. So you need to make sure that the drive is going to be capable of spinning the motor that you've got under the desired load. Make sure the voltages match, and obviously make sure that you're going to feed it the proper voltage input, right? So this rating of a drive, I'm not sure if it would fault out at 480, but I would imagine it wouldn't. I'd imagine it'd be fine if you feed it normal, like USA 480 volts at 60 hertz. But you can see this is a 20 amp drive. So obviously the little tiny motor that I've got is not really suitable for it. But you know, you see I can still run it, right? Depending on the drive, you might have issues there. You know, if you've got a 100 horsepower drive and you're trying to run a 1 horsepower motor, well, the drive might not see that small of a load as acceptable, and its internal protections are probably going to get confused and think, you know, what the hell, what small tiny load is this? And it might fault. It might give you some type of phase output fault or something like that, right? So you might run into issues there, but generally speaking, you know, if you've got a drive like this, you could probably run a motor that's only a fraction of a horsepower, right? Wouldn't push it, but at any rate, with this right here, obviously you could see you're not going to be able to really run it off 220, and you're not going to be able to feed it 600 volts. So you need to keep in mind of the voltage class. This guy right here is actually able to output up to a 600 hertz frequency, right? So here's the inside of this one. I'm sort of semi taking it apart here. You can see that it looks to use a pretty basic pre-charge circuit. So that's probably what this is right here. So you've got a set of resistors in line with the DC bus. At some point this relay basically shunts it out, right? And you know, over here you just got your little power supply section. Somewhere down in there is probably going to be, you know, like some optos and gate drivers, and you know, they're all pretty similar to a certain degree. DC bus is right under there, and you got your input terminals. This would be like your control board over here, and so basically you'd have your IO right here. So you've got some digital inputs, some analog inputs, analog output. You know, some just other terminals. So this right here is probably going to be a 24 volts supplied by the drive for, you know, your different input signals and whatnot. You've got, looks like communication right here, RS-45, then probably some form of interlock perhaps, and you know, like an enable, maybe not. And, you know, these digital inputs right here would be things like start, stop, reverse, probably, right? And so you can see right here you've got a plus and negative. So this would be terminals directly tied to the DC bus capacitors. You've got your RST, L1 through 3, the 3-phase input, and UVW motor outputs. Right here, PB, this looks to be a brake resistor input, right? Where I suppose you'd put a brake resistor right here. So if you look up the manual here for this drive, so here's a little block diagram so you can see. So if you do have a braking resistor, external one, then yeah, you'd put it across your positive and the PB right here. And it's just showing you, you've got programmable digital inputs. Default's going to be, you know, forward, reverse for these two. And you've got a common. And you can see the 24 volt right here, showing you supplied internally. You got NPN or PNP, basically sink or source. Then another common thing you can see, as with the, you know, analog input, is just showing you that you can put a potentiometer across these terminals here. So, you know, the wiper on analog N1, you got 10 volt plus on the left and then ground on the right. So for an external speed reference, then you can use a potentiometer that you just plug into those terminals, right? But of course, you know, as you can see here, this comes with a keypad that, actually this keypad, you know, uses a RJ45 connector. So you could extend that out if you wanted to, but you're going to be able to use this as well. So it's just an example. A lot of drives, most of them come with some type of keypad like this. Basically just a way for you to test the drive and have functionality at the drive. But you know, most of the time in you know, industrial applications, these are going to be controlled remotely rather than quote locally right here at the drive. Pretty much so long as you get a certain number of parameters right, then you put your motor in, you wire your motor up, and you can run that thing. But let's just say, depending on the type of drive you've got, it might require you to do some more setting up. But this is just an easy peasy generic VFD, not really having a whole lot of closed loop functionality. For example, running servo, something that requires feedback. If it's just straight induction motors, most of the time you really only need to put a few parameters in, and most of the time just factory resetting it to the defaults will get you pretty much to a state where you can run up any motor. But let's just say you're running a very small motor and the drive you're using has an overcurrent protection of a much higher rating than the motor you're actually running. Well, if there's a scenario where some type of fault inside the motor windings, then perhaps you're going to burn it out before the protection kicks in because you didn't set it properly, right? So things like that. If you want to make sure your motor's going the proper speed, well, you're going to want to set all your parameters in properly. It's like the max RPMs, the proper frequency of the line input, things like that. But otherwise, I could just power this up, wire some random 3-phase motor I've got, that this thing will run. It shouldn't have any problem either way. If I've got no type of load on it, unless it's just so gigantic that the inrush, is just too much for it or something, the thing faults out. But most of the time that's about all it is. So powered up, make sure there's no interlocks in place. A lot of times that'll just simply be the case. You're either going to need to have some stop asserted, whether it be just putting some type of signal on the stop input. You might also have a enable input, right? Some type of interlock, safe torque off might be called, sort of an industry standard there. So you might have some small roadblocks to initially get it going, but once it's in a ready state, and most of the time you just run it, stop it, adjust the speed and whatnot. This is the 3-phase VFD, but I probably could run it single phase. I would just run it off RNS, and I'm basically not using all the diodes in the 3-phase bridge rectifier at that point. So I have to derate the drive if I'm going to run it that way. But so long as I can charge that DC bus up to a certain point, then it should run all the same. It just might throw some type of phase loss fault if I don't disable that, right? But otherwise it should work. So here's actually an image I pulled off of a Invertech drive website, right? Don't really deal with them, but they're cool. So this is a pretty good one. So this is just a common schematic of a VFD, a 3-phase VFD that's got the dynamic braking in there, right? So basically you can see you've got your 3-phase input, and then you've got your 6 switches on the output. So typically this will be, you're going to have 3 half bridge modules, or you might even have just one module with all this built in, or you might even have one module with all the output switches built in, and it's also including the input rectifiers as well as the 7th switch. So this would basically be called, like a brake chopper or your 7th switch. It's just a 7th switch on top of the 3-phase inverter that's just going to chop on and off to bring that braking resistor into the circuit. You can see it's just straight across the DC bus, right? A good thing to do when testing VFDs is to do a basic diode check, right? So this basic diode check is something that you can do with pretty much all of them. And it's just checking to see if any of these switches failed, any of these passive rectifiers failed, which they're not always going to be passive, by the way. Sometimes you're going to have thyristors on the input. So you got basically big SCRs. I guess there's lots of different functions they could have. One could be for, they're going to switch on and off to serve for as a pre-charge. Or you might have some on the front that are actually part of a front end inverter for when you've got regenerative feedback, right? So that'd be a case where your braking power basically goes back to the mains, so it has to create its own inverter, match the phase, blah blah blah. So it can't be passive, it needs to be switching right. In this case, these are all passive on the front, back, even check this one right here basically. So it's as simple as putting your meter on the diode function. I'm gonna take my probes here. I'm gonna take the negative terminal, negative probe, I'm going to put it on the positive terminal of the DC bus. Then I'm going to take my positive probe and put it on L1 right here. So I'm getting this voltage drop, 0.475. Then I'm putting it on L2, 0.481, L3, 0.475, 474. Let me read this other one again, 0.481. So it's a little bit off. No big deal, right? If I was looking at too much of a change there, then I think, hey, what's going on? These are all supposed to be the same diodes, the same input module. Why is one so off? But that's not enough of a difference to be concerned over, right? So now I'm going to do the same thing, but put my positive probe on the 3 output terminals. Whoops. Actually, you saw I was charging up there because it accidentally moved my negative terminal to my negative probe to the negative terminal. So I'm basically charging up the DC bus now with my meter voltage. So I'm putting it back on the positive terminal. So negative to the positive and positive probe on one of the outputs. So I'm getting this voltage drop, 0.409. I'm checking the V now, 0.409. I check the W now, 0.409, right? So you can see basically, in this case, I'm taking the negative meter probe, right? I'm putting it on the positive of the DC bus. Then I'm taking my positive terminal. Let's just say, let me do it like this. I'm taking my positive terminal, and then I'm putting it across one of the inputs. So I put it across this, let's just say this is L1, right? When I do this, you can see I'm checking this diode right here. I'm getting the drop. Put it on L2. See, I'm checking this diode. L3, right here, checking this diode. So the top half of these diodes, what I'm able to check. Likewise, I'm doing the same thing when I'm checking the outputs here. So instead of tracing it all the way back to the leads, you can see back here. So here goes one output. So when I do that, I'm checking the reverse diode built into this switch right here. I'm doing the same thing for second output, the third output, right? So I'm checking all the diodes in the top half of the VFD. Likewise, you simply reverse this process. Now I'm going to put the negative or positive probe on the negative DC bus terminal. Just do the same thing, right? So now checking the drop there, checking the drop there, checking the drop there. Same thing on the outputs. All right, so now that I've checked all the bottom half diodes, you basically see that, okay, none of these are in a shorted condition, right? And likewise, since the breaking resistor is going to be placed right here, you've got your positive terminal, and then the collector drain. This is probably the collector of an IGBT here. So once again, you could basically check whether this switch is in a shorted position. This right here actually shows that what it has is a reverse diode right here, which would be across the resistor. So basically, if this schematic was accurate, we're going to take our so I got our positive on the positive, negative on the PB, and we're not getting a drop. And then we're going to check it the other way, and we get the drop. So getting the drop basically going like this, right? So here's another sort of common element that you might find in a lot of them. You might have a DC link reactor that is supposed to be in line or not, but they'll give you terminals for it, right? So you might end up with maybe 2 type of positive terminals for your DC bus, to where this is where you would put a DC choke, right? But if it wasn't present, then that's where you would need a jumper between those 2 points. If you don't have the jumper there, clearly you can see that you're never going to charge your DC bus, right? So when it actually comes to the dynamic braking part, I feel like a common example would be showing how a DC motor works, where you're basically just going to short the windings out and then see how that you've got a resistance there in the rotor, right? But that's technically not what's going on with these VFDs, right? A VFD is basically outputting a inverter signal to drive the motor when it's regenerating, right? So that basically means in order for it to break, it's actually outputting a frequency, right, of current that is slower in rotational speed than the rotor is actually going at the time. So if the rotor is going full bore, then in order to start braking it, the VFD is going to generate this signal that ordinarily would drive the rotor slower than that, if that makes any sense, right? So in that process, you actually get, as a byproduct of the motor slowing down because of that, you're going to generate power back into the drive. So basically what happens is you've got these diodes here that are taking that charge and putting it right back on the DC bus, right? So theoretically, depending on the type of energy you've got in this rotor, the load on it, the momentum and whatnot, I mean, you could be putting a ton of power back on the DC bus. So that's the whole point of the braking resistor. The braking resistor is there to just basically bleed off this excess power, because your DC bus is going to charge up to a certain point where, you're just surpassing the ratings of the capacitors, right? You don't want it to go over like 700, 800 volts. Most of the time, it depends on the rating of the drive, but let's just say this is a 480 volt drive. Well, you're very likely going to have a series of 400 or 450 volt capacitors, right? So this is just how it's done to save money and whatnot. It's just the most viable way to do it. But obviously you don't want to be putting like 900 volts on them then, right? One of them is going to blow up. So that's the whole point of the chopper. So you've got a sense circuitry that says, oh, voltage is getting too high. I need to start chopping this resistor across the DC bus to bleed it off, because I'm breaking this motor, right? So that's really how it works. It's not really placing the resistor directly across the windings to slow it down. That would imply that the dynamic braking doesn't involve any power. So basically what will happen a lot of times is, let's just say you've got a dynamic braking situation where you've got a big ass motor, got a lot of speed, momentum. If that thing was to just coast down, then it's gonna keep spinning for a while. And let's just say you lose power. All of a sudden you've lost power to the VFD. Well, technically speaking, it all depends, but technically speaking, that thing could generate a whole lot of power to the point where this thing could just break itself, right? So technically speaking, some type of instant slowdown would still be possible even with no power provided to the VFD, but at the same time, it's using some of that energy that was already present in the DC bus and what it's able to get back during the braking process, right? So that's pretty cool. So while that's the more basic way to do it, that's where regen drives come in, right? So a regen drive, what that's going to do is, rather than just bleed all that off into a resistor, and sometimes these braking resistors can be gigantic, right? It depends on what they're running. You got big motors running heavy stuff, you're going to have huge gigantic braking resistors that are getting super hot, right? So instead of just wasting all that every slowdown, then you have regen systems. So a lot of times what they'll do is they'll just at a base level, they've got a front end inverter where that inverter is going to send some of that DC bus and bleed it back to the grid, right? But a lot of times you'll just have a bunch of interconnected drives or something, right? You just got a shared DC bus. They can all strap together through bus bars, and then there might be intelligent ways for one motor to use some of the braking energy off one over here, while this other motor over here is using some of that braking energy to start up, or something like that, right? So there's lots of cool ways to do it, but that would be your actual regen system. So it's not really a regen unless it's putting it back on the grid, but pretty much every VFD like this is going to have the ability to regenerate power back on the DC bus when it does any form of dynamic braking, right? So a lot of them are going to have little internal braking resistors that'll be able to handle a certain amount, but let's just say you're running the largest load you can, then you might need to add an external one, which is why they'll give you those terminals, right? That will be only if it includes dynamic braking, i.e. that 7th switch, right? Alright, so I got this puny little 3-phase motor here. It's only like a 220 volt motor. And I'm just going to take this, rather than try to feed it a DC, I'm just going to take this little step down transformer and run it, wire it up for 480, run it in reverse off of 120, right? So I'm really just using this little inverter right now just because I had it handy and hooked up. So I can ramp the voltage out of that little transformer now to, let's just say, about its rating, right? So then wire this guy up. All right, so again, this is a 3P drive, but I'm just wiring up L1 and L2, the R and the S off this transformer here. Just kind of really got it jankily set up right now, but you know, whatever. And I'm going to be reading the DC volts on the DC bus, and just going to power this thing up, see at what point it will power up. So I'm just going to sort of slowly ramp it as to not pop these fuses, and see at which point. Still not on yet. About 200 volts. Should be coming on here. So there it goes. So now it's on, but I haven't heard a relay click yet. So the pre-charge is still going. So at a certain point, you're going to hear a relay click. So about 360 volts DC. Oh, there goes the relay clicking. So I'm just going to bring it to about 450 DC. And I guess at this point, I have no idea how to set this thing up. So at this point, basically, I was curious whether it was going to give me a phase loss fault, but it doesn't appear to be doing that. But actually go down here to the manual and see that I guess P9 parameter 14, so I guess program group 9 parameter number 14 is the input phase loss. So it's actually factory default to be on, but I can disable that if it actually gives me a problem, right? Alright, so I'm basically want to figure out how to set basic things like the control source, things like overcurrent, output voltage, things like that. So see right here, P003, you can select the control method. So open loop vector control probably be a pretty good way to do it. Default is volts frequency, so that's also totally fine. So I don't really need to mess with that. As far as the run command source, I want that to be the operation panel. So I would leave that at 0, so that's default. Alright, so here we got the motor settings, so this would be P4. You basically want to check the run command source. Can navigate here, so you can see I've actually found P0 here, and I'm guessing I can click that. Alright, okay. So I'm going to go to P004. Click that, and that's set to 0, which is, okay, that's the keypad, so that's good. And then I think I want to go back to P4 here. So this is the motor parameters. All I'm really going to do is set the rated voltage on here. Oops. So that will be P402. So P402, it should be on 380 right now. I'm just going to back that down to 220. Alright, so let's do 220 there. P404. Let's see. Wait, is that what I just did? Yeah, P402. Yeah, rated voltage. All right. P404. So 15 amps. Yeah. It's got to be a way for me to. Well, let's see. Shift. There we go. So let's bring that up to something like. I'm just going to do 2 amps, right? So that should be good enough. So let's see, P406 rated speed. So P406, come on now, 1440. I was going to wheel it up to 1500. Close enough already, but boom, 1500. All right, and so far, again, this thing hasn't given me phase loss. I don't know if it's going to do that at a certain point. And I'm really not sure if this thing is actually set up yet in a ready state. So I'd have to look that up. All right, so it doesn't look like there's any interlocks or anything like that. So I should be able to either just run the motor or jog it, and it looks to me like that's just kind of showing the current output speed, the current RPMs, whatever unit it is, frequency RPMs. But so if I try to jog it right now, let's see what happens. So I'm holding the button down. Oh, you can see it faulted out. So it jogged for just a second and then it faulted out. So you go ahead and hit stop now. You hear what happened. The main fan also came on as I held down the jog button. ERR23, so there goes my phase loss, right? So basically I'm going to go back to whatever parameter that was for me to enable the phase loss, or disable the phase loss fault rather. So I'm going to look up phase loss in the search. This is a weird Chinese manual that it's not really going to allow me a good menu kind of deal. All right, so here we go, P914. So if I set P914 to 0, it's allowing me to run this guy off single phase input. So I'm gonna go over to P9 and 14, and I'm gonna set that to 0, like so. Whoops. And now let's see if it's gonna let me jog it. And of course, as I hold the jog down and that spins up, you're gonna see that DC bus voltage drop a little bit, and I've got some real puny wires. Not the best setup, but we'll see what happens. Hopefully it won't dip too much. So it dipped a little bit, not too much, and you can see we're jogging. It's actually jogging it at 6 Hertz. So I've successfully disabled the phase loss, and I'm able to run this single phase, as you can see. So basically that should also mean that I can just go ahead and run it outright normally now. So I'm just going to actually increase the DC bus voltage to about 500 something here. And now I'm just going to hit the run button. So now it's running up to whatever speed I set on the keypad here. You can see I'm going to bring it down to 0. Right, then I'll just stop it, and at some point that main fan's going to shut off. So I'm just going to cut this guy off, so I'm no longer next to dangerous voltage here. And this is just sort of an example of where this is this is not an ideal test, but this is just showing it running, right? So typically I would have a much bigger motor. So this is actually 3-phase drive, very similar. It's actually set up for single or 3-phase. Right, so you really shouldn't need to disable any phase loss with this. This is a 230 input volt drive instead of a 480. This one's actually more suited to this little motor, so I'm just going to run this one. So this one is set up for single phase or 3-phase input. You can see I've just got the single phase input on L1 and L2. Shows you the little terminal legend here. So top 3 on the left are your input, top 3 on the right are your output. You've got your ground down here. I'm not really going to use it. I'm using a battery supply. You got brake resistor input number 2, brake resistor input number 1. But then as you can see right here, you've got a +2 and a +1. So these 2 bottom right terminals here, that would probably be where a DC link choke would go right here, right? But as you can see, with no choke present bridging those terminals, then they've actually just got this shunt right here. So this little jumper right there is serving the purpose, so you would replace that with the DC link. So just again, for example, if that wasn't there right now, then you're actually not going to be able to charge the DC bus. So I'm just going to sort of go through the same process. I've got the AC voltage. I'm reading on it now. So I just want to feed this one, maybe like 220 volts AC. So I'm going to start cutting that one up until I reach about 220 AC. And you can hear the little relays kicking on and whatnot. So yeah, I'm going to leave it like right about there. So now we're on, and you can actually see this one is probably already set up for the keypad. So see, I can adjust it up to 60 Hertz or down to 0. You also got a program. So you can actually see that brings you to these pars right here. So I'm guessing I can go through the group. So let's just say Max operating frequency right here, 0.00, so 1-00 max operating frequency is 60 hertz, right? So that's good. Press mode to get out of there. So that's how you cycle through the parameters. And I'm just going to hit run, see if it runs. So yeah, it's running now. So kind of get some pretty fine control on there. And stop it. Then, as you can see, once again, I've got these control terminals. So you've got a 10 volt for your analog input. So you could probably use a potentiometer to control the speed as well. And then you got some of these other terminals here. Those are probably output signals for something. And let's see, M1, M2, M3, M4. I imagine those are your input, your digital inputs. So, it's the same general idea, right? But you can see it's just little different method of setting the parameters, but more or less just power the thing up, set some parameters, and then it's pretty much good to go. Now, this doesn't say anything about current, sort of a puny VFD, puny motor, but ordinarily I'd want to at least set, current limits and things like that, right? Pretty cool. So let's set it to 60 and run it, and you'll see it doesn't really just immediately kick off full bore. Kind of ramps up because there's an acceleration time. So actually, let's see if we can look this up to see if we can set it to stop a different way, right? Just as an example. All right, so here goes the manual for this particular guy right here, and I'm basically just going to look for the parameter to set up the braking here. So it doesn't really look to have a good menu, so I'm just going to have to search for it here. Alright, so if I actually look up just the word coast, then it's going to bring me straight to this stop method here. But it's actually set up, this is the factory setting, it's actually already set up to ramp to stop. And I would imagine this means the external frequency source that would be coast to stop. But since I'm locally setting the speed reference with the potentiometer on the keypad, it's actually set to ramp to stop. So that means it has a slow decel time, which, as you can see, is actually factory set to 10 seconds. So if I actually go to parameter 110, and let's just say I set that to 1 second, and instead of a 10-second slowdown, it should stop immediately within a second. So now that I've set that parameter, I think it was 110. So 110, boom, I've set it to 1 second now, right? So let me back to the frequency. And now when I run it up to the maximum frequency, let it get up to 60 hertz. And it's about there now, about 1500 RPM. Then now when I hit stop, it's not going to take 10 seconds. Boom, took 1 second, right? And during that time, that DC bus would have slightly charged up a little bit, but we're not talking about a huge load here in this rotor, right? So it wasn't a big deal.